confine the Great Red Spot, how turbulence erodes its boundary, and why a deep storm can survive even as it shrinks at the cloud tops. Before settling in, please like the video, subscribe to the channel, and let Jupiter's quiet weather carry the night gently forward. Jupiter sits far from the Sun compared with the inner planets, yet it dominates the solar system by mass and by influence. It is a gas giant, a world without a solid surface in the ordinary sense, built mostly from hydrogen and helium and wrapped in a deep atmosphere that blends gradually into denser fluid layers below. Its gravity shapes the orbits of countless smaller bodies, and its presence helps define the architecture of the asteroid belt and the paths of comets. In the quiet background of planetary motion, Jupiter acts as a major organizer, a central weight that steadies and disturbs in different ways depending on where an object travels. The scale of Jupiter is immediately different from the terrestrial planets. It is the largest planet in the solar system, with a diameter so large that Earth could fit across it many times. Its volume is vast, and its mass is more than all the other planets combined. Yet it is not a solid sphere of rock. It is a layered, fluid planet, where increasing pressure and temperature with depth change the behavior of gases into liquids and, deeper still, into exotic states of matter. This layered fluid nature is one of the reasons Jupiter can host enormous weather systems that persist far longer than storms on Earth. There is no coastline, no mountain chain, and no land friction to break a storm's circulation. There is only atmosphere moving across itself in bands and vortices. Jupiter also rotates quickly. A day on Jupiter lasts only about 10 hours, so the planet spins much faster than Earth. Fast rotation matters because it strengthens the Coriolis effect, the tendency for moving air to curve due to rotation. On a rapidly rotating planet, large-scale flows organize into east-west bands, and storms can become long-lived vortices trapped between strong jet streams. Rotation shapes the entire visible face of Jupiter, from its alternating bright zones and darker belts to its stable, persistent storm systems. The Great Red Spot exists inside this broader rotating environment, not as an isolated event, but as a feature embedded in a planet-scale circulation. The energy budget of Jupiter differs from that of a rocky planet. Sunlight reaches Jupiter, but it is weaker there than near Earth because Jupiter is farther from the Sun. Even so, Jupiter is not a cold world powered only by distant sunlight. Jupiter radiates more energy than it receives from the Sun, indicating a significant internal heat source. This internal heat is a remnant of formation and slow contraction, released over time. It rises from the deep interior and drives convection, the upward movement of warmer material and the sinking of cooler material. Convection supplies motion and instability to the atmosphere. It provides a constant background of energy that can feed storms from below, sustaining them when sunlight alone might not be enough. The atmosphere of Jupiter is also large in vertical extent. What appears as a cloud top in images is only a layer where certain gases condense into visible clouds. Above and below these clouds, the atmosphere continues, with changing temperature, pressure, and composition. The main visible cloud layers are associated with compounds such as ammonia and ammonium hydrosulfide and with water deeper down. Though the water cloud level lies far below the highest visible hazes, the visible bands reflect differences in cloud thickness, particle properties, and vertical motion. Bright zones often correspond to rising air and thicker clouds, while darker belts often correspond to sinking air and thinner clouds that reveal deeper, darker layers. This banded structure is not fixed like paint. It shifts and evolves. yet it maintains an overall pattern shaped by rotation and internal heat. In this setting, a storm is not simply a patch of cloud, it is a three-dimensional circulation, a vortex that can extend downward and interact with surrounding winds. The Great Red Spot is the most famous example, but it is not the only long-lived vortex on Jupiter. The planet hosts many smaller ovals and storms that form, merge, and dissipate. Some persist for years, some persist for decades. The Great Red Spot persists for centuries in the observation record, making it a rare and valuable laboratory for atmospheric dynamics. It offers a stable target for repeated measurement, allowing scientists to watch slow change in a system that is otherwise in constant motion. Jupiter's atmosphere lacks a solid lower boundary that would strongly limit how deep a storm can go. Instead, storms interact with deeper layers where gases become denser and where the distinction between atmosphere and interior becomes gradual. A vortex can, in principle, extend downward until changing density, changing composition, and changing electrical conductivity alter the flow. At some depth, the properties of hydrogen shift under pressure and conductivity increases. Magnetic effects can become important. These deeper regions are far beyond direct imaging, yet they matter because they can provide a deeper anchor for circulation, or can act as a damping region that resists certain motions. Understanding whether the Great Red Spot is a shallow feature near the clouds or a deep structure reaching far below is central to understanding how it survives and how it changes. The Great Red Spot's shrinking, the focus of the title, is therefore not simply a surface story. It sits inside a planet-scale system defined by gravity, rotation, internal heat, and deep atmospheric layering. Shrinking can mean changes in the visible outline, but the physical storm may have a vertical extent and internal structure that do not shrink in the same way. A storm can lose area at its cloud-top expression while remaining deep and energetic below. A storm can also become more compact while maintaining strong winds. These possibilities exist because a vortex is a rotating fluid structure, not a rigid object. It changes through interaction with its environment. Jupiter's environment includes strong jet streams that circle the planet. These jets are alternating bands of eastward and westward winds. They can be stable for long periods, yet they also vary with time and latitude. The Great Red Spot sits in a region where surrounding jets confine it, acting like boundaries that keep the vortex from drifting freely north or south. The jets also shear its edges, stretching and compressing the storm. This is part of the physical reason a long-lived storm can also slowly change shape. The storm is trapped, but it is not protected from stress. It is surrounded by moving air that can peel away filaments, inject smaller vortices, and change the energy balance at its edges. The chemistry of Jupiter's upper atmosphere adds another layer of meaning. The Great Red Spot is red, but Jupiter's clouds are mostly pale, with white, tan, and brown bands. The red hue is thought to be related to complex molecules or particles in the upper haze that are altered by sunlight and by energetic particles, and then carried upward by the storm's circulation. The colour can change over time, becoming deeper or paler. Colour is not only decoration, it is a clue to altitude, to mixing, and to chemical processing. A storm that changes in strength or in vertical reach can change the altitude at which coloured particles reside, and this can alter how the storm looks even if the underlying circulation remains strong. Jupiter's role in the solar system also shapes how it is observed. The planet is bright and large enough in the sky for small telescopes to show its bands. Larger telescopes reveal finer structure, including the Great Red Spot's outline and its surrounding turbulence. Spacecraft add still more detail. measuring temperatures, wind speeds, and composition, and in some cases probing depth through gravity and microwave sensing. The long record of observation, from early telescopic sketches to modern imaging, provides a rare timeline for a planetary storm. It allows the idea of shrinking to be grounded in measurement rather than impression. The change is not a single event. It is a trend observed across decades, set within a storm that remains persistent. This first region holds Jupiter as a whole because the storm cannot be understood without the planet that hosts it. Jupiter is massive, rapidly rotating, internally heated, and deeply layered. Its cloud tops are only the visible skin of a vast fluid world. Within that world, long-lived vortices can form and persist, confined by jet streams and fed by energy rising from below. The Great Red Spot exists as one such vortex, famous because it is large and because it endures long enough for slow change to be noticed. Shrinking becomes meaningful only against this background of planetary scale and planetary physics. The inward path now moves from Jupiter's global context to Jupiter's visible face, where the banded clouds and the Great Red Spot appear as patterns in light. That next region remains at the cloud top level, establishing what is seen and how the storm sits within the moving belts and zones. From far away, Jupiter presents a striped face. Bright bands and darker bands wrap around the planet in parallel lines, bending slightly with curvature and shifting subtly with time. This banded pattern is the first clue that Jupiter's atmosphere is not random weather but an organized circulation. The organization comes from fast rotation and from the way rising and sinking air is arranged by that rotation into broad belts and zones. Within this moving pattern sits the Great Red Spot, a large oval storm that stands out by colour, by shape, and by its long persistence. The visible bands are made of clouds and hazes at different altitudes. The brightest regions, often called zones, tend to contain thicker high clouds that reflect more sunlight. The darker regions, often called belts, tend to have thinner or deeper cloud decks, allowing darker material below to show through. These names describe appearance rather than fixed composition, because Jupiter's cloud layers and haze layers are complex and vary with time. Yet the general pattern remains. The belts and zones are tied to jet streams, fast winds that circle the planet in alternating directions. Some jets move eastward relative to Jupiter's rotation, and others move westward. The boundary between a belt and a zone often corresponds to a jet, where wind speeds are high and where shear is strong. Shear is a difference in wind speed across a short distance. It is important because it can stretch clouds into long filaments and can help maintain sharp boundaries between bands. Shear can also help stabilize large vortices by confining them between jets. A vortex that tries to move north or south can encounter different wind regimes that push it back or tear it apart. The Great Red Spot resides in such a confined latitude band, where the surrounding jets act like rails on a track. The storm remains near the same latitude for long periods because the broader circulation keeps it there. The Great Red Spot is an anticyclone, meaning its rotation corresponds to high pressure relative to its surroundings in the meteorological sense used for Jupiter. On Jupiter, pressure is not measured against a solid surface as it is on Earth, but relative high pressure and low pressure systems still exist as patterns of vertical motion and circulation. An anticyclone tends to have air that rises at its center and sinks around its edges, though the exact vertical pattern can vary with depth and with the structure of the vortex. The visible consequence is that clouds inside the storm can be higher than surrounding clouds, and the storm can have a distinct boundary defined by strong winds. In images, the Great Red Spot appears as an oval set into the southern hemisphere's banded pattern. It is often bordered by a pale region and by turbulent wake structures where surrounding winds interact with the vortex. The storm is not isolated by empty space. It sits in a crowded atmosphere where smaller storms form and drift. Bright plumes and dark streaks pass nearby. The belts and zones that surround it can change in brightness and in width over time, and the storm's own outline can shift with these changes. The Great Red Spot therefore exists as a stable vortex in a changing environment. The storm's red colour is most prominent in visible light. Its hue can vary from pale orange to a deeper brick red. The colour is not uniform across the storm. The central region can appear smoother and more uniform, while the outer region often shows swirling patterns, streaks, and scalloped edges. The boundary is a region of strong winds that can be traced by cloud features moving rapidly around the perimeter. The interior can show slower patterns and large-scale flow. The contrast between the red oval and the surrounding white and tan clouds makes the storm easy to identify, even when its size is changing. Cloud patterns on Jupiter move quickly, because Jupiter rotates fast. The planet's visible features sweep across the disk within hours. Yet the Great Red Spot remains identifiable from one rotation to the next. Over days and weeks, its position in longitude shifts slowly relative to a fixed coordinate system because the surrounding winds and the storm's drift are not perfectly locked. Over longer time, the storm's shape changes slowly. This slow change stands out against the rapid motion of smaller cloud features and the constant streaming of jets. Observations of Jupiter from Earth rely on reflected sunlight, and they are influenced by Earth's atmosphere. Even with excellent telescopes, the finest details are blurred by turbulence in Earth's air, though modern techniques can correct some of this. Space-based telescopes avoid that blurring, and spacecraft provide the highest detail. Yet even modest telescopes can show the Great Red Spot and can show that it changes. The fact that the storm is visible to small instruments is one reason it has such a long observational record. Observers have watched it for generations, drawing its outline and noting its drift and colour changes. This record provides context for the modern claim that the storm is shrinking. Shrinking at the cloud top level is seen as a reduction in the storm's apparent size compared with the surrounding bands. Historical drawings and early photographs suggest that the Great Red Spot was once much larger in the east-west direction than it is today. In more recent decades, the storm appears to become smaller and more rounded, with a reduced length and a more compact oval shape. Modern measurements show that this change is not a matter of a few days. It is a trend observed over many years. The cloud-top view provides the simplest evidence. The storm occupies fewer degrees of longitude than before. Its boundary looks tighter. Its shape looks more circular than the elongated oval often depicted in older records. The cloud-top view also reveals another change: the storm can shed filaments. The edges sometimes peel off into long reddish streamers that stretch into the surrounding belts. These streamers can wrap around and mix into nearby turbulence. Such shedding events suggest that the storm exchanges material with its surroundings. It is not sealed. It can lose coloured particles and cloud material, and it can also gain energy and material when smaller vortices merge with it. The visible face of Jupiter therefore shows not only a stable oval, but also ongoing interaction. The belts and zones themselves change with time in ways that can influence the storm's appearance. Jupiter's belts can fade and then return. Their colours can shift, their widths can change. The surrounding flow can become more turbulent or more smooth. When the background changes, the contrast with the Great Red Spot can change, making the storm look more prominent or less prominent, even if its size is similar. A careful interpretation separates true geometric change from changes in contrast and colour. The storm's shrinking is supported by measurement, not only by impression, but the cloud-top view remains sensitive to how clouds and hazes are illuminated and how the background evolves. At this cloud-top level, the Great Red Spot is also a marker of time. A feature that endures long enough to be watched for decades becomes a reference point. It allows scientists and observers to compare the behavior of other features in Jupiter's atmosphere against a stable anchor. When other storms appear and disappear, the Great Red Spot remains. When belts change in brightness, the Great Red Spot remains. This persistence makes its slow shrinking and reshaping meaningful. It is a change in a feature that seems permanent in everyday human observation. The cloud-top world of Jupiter is therefore a moving canvas. Fast jets create bands, shear shapes boundaries, vortices form and drift. The Great Red Spot is the largest and most persistent vortex in this visible layer, sitting between strong jets, coloured by chemistry and haze and interacting with nearby turbulence. Its shrinking is first noticed here, in the reduction of its visible outline and in the change of its shape from a broader oval to a more compact form. This cloud-top picture is essential, but it remains only the surface expression of a deeper system. The inward path now moves from the visible face to the long observation record and the modern measurements that quantify the storm's change. That next region anchors shrinking to specific kinds of evidence, showing how the record is built and what it can and cannot prove about what is happening beneath the clouds. The Great Red Spot is unusual in planetary science because it carries a long record. Many features on planets are transient. Jupiter's belts shift, storms appear and fade, and smaller ovals merge or disperse. The Great Red Spot persists through these changes, leaving a trail of observations that span centuries. This record is uneven in detail, because instruments improve over time and because early observers rely on drawings rather than photographs. Yet the record is still valuable. It provides a timeline of what the storm looks like at the visible cloud tops and how that appearance changes. Early telescopic observations of Jupiter reveal that prominent spots and ovals exist. But the historical identity of the Great Red Spot through the earliest centuries is not perfectly continuous. Observations indicate that a large spot in Jupiter's southern hemisphere is seen in the 19th century, with enough consistency to match the modern Great Red Spot's location and behaviour, and that by the late 19th century the feature is well established in the record. From that point onward, the storm is observed repeatedly, with increasingly reliable imaging. The record becomes strong enough that changes in size and shape can be compared across decades rather than across isolated sketches. Photographic records in the 20th century improve consistency. Photographs reduce the interpretive variation of hand drawings and allow direct measurement of the storm's dimensions in image coordinates. As imaging technology advances further, digital measurements provide even more precise tracking. Modern telescopes and spacecraft produce images where the storm's outline can be mapped in detail, and the motion of cloud traces can be measured to infer wind speeds around the boundary. These tools turn the Great Red Spot into a measured object rather than a purely visual impression. When people say the storm is shrinking, they often refer to its east-west length. Early measurements and historical images suggest that the storm's long axis once spans a much larger portion of Jupiter's disk than it does today. Over the 20th century and into the 21st, the measured length decreases. The storm becomes less elongated and more compact. The reduction is large enough that it cannot be explained by small changes in viewing geometry alone. It appears as a real change in the storm's visible extent. The record also shows changes in shape beyond simple length. The storm's outline varies. It can appear more oval at times, more circular at other times. The edges can become more scalloped, with small protrusions and indentations that reflect interaction with surrounding turbulence. At times, the storm sheds ribbons of material into the surrounding belts, producing visible red streamers. At other times, the boundary appears smoother. These changes indicate that the storm's cloud top expression is dynamic even while the overall vortex persists. The shrinking trend is therefore embedded in a more complex pattern of short-term variability. Colour is another part of the record. The great red spot's hue changes over time. It can appear paler for periods and then deepen in colour. Observations indicate that changes in colour do not always track changes in size in a simple way. Colour depends on haze chemistry, on altitude of cloud tops, on sunlight-driven reactions, and on the mixing of material from deeper layers. A smaller storm could appear deeper red if its vertical circulation lifts coloured particles higher or maintains them in sunlight. A larger storm could appear paler if its haze layer changes. Therefore, colour is recorded alongside size, but it is not a direct proxy for shrinking. It is a separate observable that can indicate changes in vertical structure and chemistry. The modern era adds another kind of record spacecraft close passes. Spacecraft observe Jupiter from near range, capturing high-resolution images and measuring temperatures, composition, and gravity. These measurements provide context for the cloud top record. They can reveal whether the storm's winds strengthen or weaken, whether its temperature structure changes, and whether it has a deep root that might persist even as the top shrinks. The record becomes multidimensional. It includes shape, size, color, wind speed, and depth clues. The record also reveals that Jupiter's atmosphere experiences cycles and variations that can influence the storm. The belts can change in brightness and thickness. The surrounding jet streams can shift slightly. Smaller storms can appear and interact with the Great Red Spot, sometimes merging with it, sometimes skimming past and stripping its edges. These interactions are part of the storm's history. The record shows that shrinking is not a steady, smooth contraction without interruption. It is a long-term trend that occurs through episodes of interaction and adjustment. One of the clearest modern observations is that the storm's visible area decreases even while its wind speeds around the perimeter can remain high. This suggests that shrinkage is not simply a weakening of the storm in the sense of losing all circulation. A vortex can become more compact while maintaining strong winds. In fluid dynamics, a smaller vortex can spin faster at its boundary, depending on how energy and angular momentum are distributed. Jupiter's storm is not a rigid object, so changes in size and wind speed can be decoupled. The record therefore contains a clue that the storm is reorganizing, not simply fading. Another part of the record is that the storm's drift in longitude changes slowly over time. Jupiter has different rotation rates used for different latitudes, because the atmosphere differentially rotates, meaning different bands rotate at different rates, relative to an internal reference. The Great Red Spot's drift relative to these systems provides information about its interaction with surrounding flows. Changes in drift can indicate changes in the background jet structure, or changes in the storm's own momentum balance. The record shows that the storm's position is not fixed like a painted mark. It is part of a moving atmosphere, and its long-term behavior includes drift as well as size change. This observational history is the foundation for asking what is really happening. The shrinking is not a rumor. It is a measured change in the storm's visible dimensions. Yet observation history also teaches caution. Early records have uncertainty in exact scaling. Drawing accuracy varies. Imaging resolution varies. Even in modern images, defining the storm's boundary can depend on wavelength and contrast. because different filters reveal different cloud and haze layers. A boundary traced in one wavelength may not match exactly a boundary traced in another. This is why modern analyses often use consistent measurement methods across time and use multiple wavelengths to understand how the storm's outline is defined. The record therefore provides two simultaneous truths. The Great Red Spot has a long-lived identity as a persistent vortex in Jupiter's atmosphere. Its visible outline has become smaller and more compact over the modern measurement era. At the same time, the storm's appearance varies on shorter timescales, and its measured dimensions can depend on how they are defined. The shrinking trend remains robust, but understanding its meaning requires defining the measurements precisely and then connecting them to the physics of a deep vortex embedded in strong jet streams. The inward path now moves to that definition. The next region clarifies what shrinking means in terms of length, width, area, shape, color, and circulation, and it separates cloud-top appearance from the deeper structure that might persist even as the visible shape changes. Shrinking is a word that sounds simple, yet for a planetary storm it contains several different measurements. A storm has an outline, but the outline is not a solid boundary like the edge of a rock. It is a region where winds, clouds, and hazes change rapidly. The Great Red Spot is a vortex, and a vortex can change its visible footprint while maintaining a deep circulation. To understand what shrinking really means, the measurements must be separated and described carefully: the storm's length and width, its total area, the sharpness of its boundary, the strength of its winds, and the changing color and texture of the clouds that mark its presence. The most common measure in the historical record is the east-west length of the Great Red Spot. Because the storm is elongated, its long axis is easy to compare across images. When older records show a larger long axis than modern images, shrinking is often described as a reduction in length. This measure is straightforward in concept. It is the distance from the storm's eastern edge to its western edge, often described in degrees of longitude on Jupiter or in kilometers once the mapping is done. The challenge is that edges are not perfectly sharp. The storm's periphery contains filaments and surrounding turbulence that can be included or excluded depending on the definition. The north-south width is another measure. The Great Red Spot sits between jet streams, and its width is constrained by the latitude range where it can remain stable. Measurements indicate that width has also changed, but the most striking change is often in length. A vortex can become more circular by shrinking more in the long dimension than in the short dimension. This would change the shape and can be seen as the storm becoming less stretched. Modern images often show the storm as more compact and closer to circular than in many older depictions. This is a geometric summary of multiple changes: length, width, and boundary curvature. Area is a third measure. Area can be estimated by tracing the outline and calculating the enclosed region. Area is sensitive to how the outline is chosen, because small changes in boundary placement can change area noticeably. Yet area can capture a meaningful trend because it integrates both length and width. A reduction in area implies that the storm's visible footprint, as marked by cloud and haze patterns, occupies less of Jupiter's atmosphere at the cloud top level. Shape descriptors add another layer. The storm can be characterized by its aspect ratio, the ratio of length to width. It can be characterized by how smooth its boundary is, whether it is a clean oval or a scalloped form with lobes and indentations. It can also be characterized by whether it has a clear central region with a quieter texture surrounded by a more turbulent ring. The Great Red Spot often shows a central region that appears smoother, and an outer ring where winds are strongest and where clouds form streaks and filaments. Changes in the appearance of this ring can affect how the storm is measured. because the ring defines the boundary in many images. Wind speed is a separate measure from size. The winds around the Great Red Spot's periphery can be measured by tracking clouds as they move. The strongest winds are often near the boundary, where the vortex's rotation is fastest. A storm can shrink in visible size while its boundary winds remain strong, or even increase in speed, depending on how the vortex reorganizes. Therefore, shrinking does not automatically mean weakening in the simple sense. A smaller vortex can still be intense. The key question is whether the total circulation energy decreases or whether the vortex is becoming more compact while retaining energy. Circulation strength can be described in different ways. One way is to consider vorticity, the measure of local rotation in a fluid. Another is to consider the integrated circulation around a loop. In practice, observational studies often focus on wind speeds at different radii and on how those wind profiles change over time. If winds weaken across the boundary, this suggests the vortex is losing strength. If winds remain strong while the boundary moves inward, it suggests the vortex is tightening. In both cases, the visible outline can shrink, but the internal state differs. Color is also a measurable property, though it is more complex. The Great Red Spot's red hue likely arises from chemical products and haze particles influenced by sunlight and by vertical mixing. The depth of the red color can change when the altitude of hazes changes or when the chemistry of the upper atmosphere changes. Color can also be influenced by changes in the surrounding belts and zones. A storm can look redder because the background looks paler, or it can look paler because the background looks darker. Therefore, color must be compared using consistent image calibration and, ideally, multiple wavelengths. Changes in color can indicate changes in chemistry and altitude, but they do not directly define shrinking. There is also the question of height. The top of the Great Red Spot may be higher than surrounding clouds, and its top can be colder because higher altitude in Jupiter's atmosphere often corresponds to lower temperature. Temperature maps can reveal this. If the storm's cloud tops rise or fall, its temperature signature can change. A higher top might indicate stronger upward motion, while a lower top could indicate weaker uplift. Yet this relationship is not always simple because temperature is influenced by radiation and by surrounding dynamics. Still, height and temperature provide additional ways to describe what is changing beyond the outline. Another important distinction is between the visible boundary and the deeper vortex. The cloud top outline is marked by certain cloud layers and haze distributions. The vortex may extend downward far below these layers, with a different shape at depth. A storm can shrink at the top while remaining deep, or it can thin in depth while the top remains visible. Without depth measurements, cloud top images alone cannot distinguish these possibilities. This is why modern missions that probe depth are important. They provide a way to connect shrinking at the surface to changes in the three-dimensional structure. In the term shrinking, therefore, at least three questions are implied. First, is the visible footprint smaller? Second, is the vortex's dynamical strength weaker, stronger, or reorganized? Third, is the storm's depth changing? The observation record answers the first question with confidence. The visible footprint has reduced over the modern era. The second question is more nuanced and depends on wind measurements and on how energy is exchanged with the surroundings. The third question requires depth probes and remains the hardest. It is addressed through indirect methods such as thermal structure and, more recently, gravity and microwave observations from spacecraft. A careful definition also acknowledges measurement uncertainty. The storm's boundary is not a sharp line. Filaments can be included or excluded. Images in different wavelengths can show different boundaries because they see different cloud layers. Seeing conditions and processing can influence apparent edge sharpness, yet the long-term trend remains. The measurements, when done consistently, indicate that the storm's long axis and area decrease. The storm appears more compact and often more circular than before, with shrinking defined as a set of distinct measurements rather than a single vague impression. The inward path can now move into the immediate physical environment that shapes those measurements, the jet streams and shear zones around the Great Red Spot. These surrounding winds confine the storm, feed it, and also erode it, and they are the first place where the mechanics of shrinking becomes visible in motion. Around the Great Red Spot, Jupiter's atmosphere moves in strong, organized streams. These streams are jet winds that circle the planet, flowing mostly east-west. They form the backbone of Jupiter's banded appearance, and they provide the immediate environment that confines the storm. The Great Red Spot sits between two such jets in the southern hemisphere. One jet flows in one direction on one side of the storm, and another jet flows in the opposite direction on the other side. This arrangement traps the vortex in latitude, like a rotating wheel held between two fast belts of moving air. It also places the storm under constant stress, because the jets shear its edges. Shear is a gradient in wind speed and direction. When two nearby flows move in different directions or at different speeds, the boundary between them becomes a region where clouds are stretched into filaments and where turbulence can form. The Great Red Spot lives within such a shear environment. On its northern side, a jet stream moves at high speed. On its southern side, another jet moves in the opposite direction. The storm's own rotation must coexist with these flows, which means its outer boundary is not simply a circle of self-contained motion. It is a boundary where the vortex's circulation meets the surrounding jets and where the difference in motion can strip away material. The jet streams also help stabilize the storm. A vortex on a rotating planet can drift north or south due to interactions with the background flow and due to the planet's rotation. The Great Red Spot's location is stable because the surrounding jets act as barriers. If the storm tries to expand into one jet, it is met by strong opposing flow. If it tries to expand into the other, it is met by the opposite flow. The result is confinement. The storm's north-south width is limited by the spacing between these jets. This is one reason why the storm's width cannot grow without limit, and why changes in jet position and strength can influence the storm's shape. At the cloud top level, the jets are visible in the motion of cloud streaks and in the boundaries of belts and zones. High-speed winds create long parallel streaks that wrap around the planet. Near the Great Red Spot, these streaks bend around the vortex, forming a wake pattern. The wake resembles the flow of a river around a boulder, with eddies and turbulence downstream. This analogy is limited because Jupiter has no solid obstacles, but the flow pattern is similar in the sense that the storm acts as an obstacle to the jet's smooth passage. The jets must divert around it, and the diversion creates regions of enhanced mixing and turbulence. This wake region is important for shrinking. If the storm loses material at its edges, that material can be stretched into filaments and carried away by the jets. Observations show that the Great Red Spot can shed reddish streamers that peel off from its outer boundary. These streamers can extend far into the surrounding belts before they mix and fade. The jets provide the conveyor belts that transport these filaments away. In this way, the jets can act as an erosion mechanism. They do not destroy the vortex in one moment, but they can gradually strip its outer layers, reducing the visible footprint over time. The balance between confinement and erosion is subtle. Strong jets can protect the storm by maintaining a stable corridor where it can sit, and by preventing it from drifting into regions that might disrupt it. The same strong jets can also apply strong shear that strips the storm's perimeter. If the jets intensify, or if their relative positions shift slightly, the stress on the storm can change. A small change in the background flow can alter how the storm's boundary interacts with the jets, potentially changing the rate of filament shedding and the shape of the storm. This is one reason why the shrinking trend can proceed through periods of faster and slower change rather than as a perfectly steady contraction. The storm itself also influences the jets. A large vortex can alter the flow around it, affecting the local jet profile. The interaction is not one way. The storm and jets form a coupled system. The storm can exchange momentum with the jets through wave-like disturbances and through the emission of filaments. The surrounding flow can feed energy into the vortex or take energy out depending on the direction of interaction. In fluid dynamics, vortices can gain energy from shear if the shear is configured to reinforce their rotation, and they can lose energy if the shear is configured to oppose it. On Jupiter, the details depend on the storm's position relative to the jets and on the vertical structure of the flow. Even without all details, the observed fact remains that the Great Red Spot exists at a boundary between strong opposing flows, making it a long-lived feature under constant dynamic influence. Jet streams on Jupiter are not static. Their speeds can vary with time and with depth. The cloud-top jets are measured by tracking visible features, but the jets likely extend downward as well, though their structure can change with depth. The Great Red Spot's own circulation extends downward to some extent, and the degree of coupling between the vortex and the jets at depth can influence its longevity. If the storm is deep, it may be less sensitive to short-term changes in cloud-top jets, because its mass and momentum extend below the visible layer. If it is shallow, it may be more easily affected by cloud-top shear and turbulence. This is why depth matters for understanding shrinking. A deep vortex might persist while its visible top is gradually sculpted by the jets. Another feature of the jets is that they can support waves. Wave patterns can travel along the boundaries of belts and zones. These waves can interact with vortices, transferring energy and momentum. Near the Great Red Spot, wave activity can contribute to the complex texture of clouds and to the formation of smaller vortices. Such activity can be a source of turbulence that nibbles at the storm's edges. It can also be a source of organized motion that helps maintain coherent flow. In a sleep-friendly perspective, these are slow, large motions, not violent chaos. Yet they matter because they set the background against which a storm either grows, holds steady, or shrinks. The confinement corridor between jets also sets the storm's maximum width. If the jets move closer together over time, the corridor narrows, and the storm may become narrower. If the jets move farther apart, the corridor widens, and the storm could, in principle, widen. Observations of the storm's width over decades indicate change, though the most prominent shrinking is in length. Changes in corridor width can still influence the storm's shape by changing how much space it has to expand in latitude. Even if width does not change dramatically, a small narrowing can increase shear at the storm's edges, potentially increasing erosion. Therefore, jet geometry is one possible contributor to the shrinking trend. The Great Red Spot also interacts with a nearby region of complex turbulence and smaller storms. These smaller vortices can be swept by jets into the storm's vicinity. Some pass by, some merge, some chip away at the outer boundary. The jets guide these interactions by setting the paths along which features travel. This neighborhood interaction is the next inward layer. It provides the mechanism by which the storm can lose or gain energy in discrete events, rather than only through continuous shear. To understand shrinking, It is therefore necessary to watch not only the jets, but also the smaller vortices and turbulent eddies that live around the Great Red Spot. This section holds the storm at the boundary between powerful jet streams. The jets confine it, keeping it in a stable latitude band. The jets also shear its edges, stripping filaments and transporting material away. Confinement and erosion occur together. The balance between them shapes whether the storm maintains size, shrinks slowly, or changes shape. With this boundary environment established, the inward path now moves to the storm's neighborhood dynamics, the smaller vortices and turbulent interactions that can feed the Great Red Spot or erode it in episodes, shaping the shrinking process in a more direct and visible way. Near the Great Red Spot, Jupiter's atmosphere is busy with smaller storms. Some are compact ovals, some are elongated streaks that roll into vortices, some are bright plumes that rise and spread. Together they form a neighborhood of turbulence that constantly brushes the Great Red Spot's perimeter. In a fluid system, a large vortex does not live in isolation. It exchanges energy and momentum with smaller eddies and nearby vortices. On Jupiter, this exchange can be seen as events where smaller storms approach, interact, and then either merge with the Great Red Spot or tear away pieces of its edge. These neighborhood dynamics provide a practical pathway for shrinking. The large storm can be gradually eroded by repeated encounters and by the shedding of filaments into the surrounding flow. A vortex is a rotating region in a fluid. Vortices can attract or repel depending on their relative spin and their position. Vortices with the same rotation sense can merge more readily, forming a larger vortex. Vortices with opposite rotation sense can interact in ways that distort and weaken each other. On Jupiter, many long-lived ovals share the same broad sense of rotation at a given latitude band, shaped by the planet's rotation and the surrounding jet structure. The Great Red Spot is an anticyclone, and nearby anticyclones can, in principle, merge with it if their paths bring them close enough and if the surrounding flow allows the merger. Mergers can add energy to the Great Red Spot. When a smaller vortex merges into a larger one, it can increase the larger vortex's circulation and help maintain its strength. This is sometimes described as feeding the storm. Feeding does not mean that the storm takes in matter like an organism. It means that the storm absorbs the organized rotational motion of another vortex. On Jupiter, such events can be visible as a smaller oval approaching the Great Red Spot and then being drawn into its outer boundary, disappearing as a distinct feature while the larger storm's boundary adjusts. At the same time, interactions can be erosive. When a smaller storm passes close without merging cleanly, it can distort the Great Red Spot's boundary. It can peel off streamers and cause the perimeter to shed material into the surrounding flow. The shedding can appear as reddish filaments that stretch away and then mix into nearby belts. Each shedding event removes some of the storm's outer cloud and haze pattern. If the storm is not replenished at the same rate, the net effect over time can be a reduced visible footprint. Shrinking can therefore be seen as a cumulative effect of many small interactions rather than a single dramatic collapse. The neighborhood dynamics also include turbulence that is not organized into clear vortices. The region around the Great Red Spot often shows swirling patterns and chaotic textures where the jets bend around the storm. This turbulence can create small eddies that spin off from the boundary. In fluid dynamics, a strong vortex can shed vorticity into its wake, producing a trail of smaller rotating structures. On Jupiter, the wake region downstream of the Great Red Spot can show a chain of features, including small dark spots and bright patches that evolve rapidly compared with the main vortex. This wake is part of how the storm interacts with the surrounding jets. It is also a region where energy is dissipated into smaller scale motion and then into heat. Dissipation is the slow conversion of organized motion into random motion and then into heat. In an atmosphere, dissipation occurs through turbulence at small scales and through radiative cooling. Jupiter's atmosphere is a low viscosity fluid at large scales, meaning it does not strongly resist flow the way honey does. Yet dissipation still occurs, and it tends to occur most strongly where shear and turbulence are strong. The Great Red Spot's perimeter is such a region. Filament formation, eddy shedding, and mixing at the boundary are all pathways for dissipation. If dissipation at the boundary exceeds the energy supply that maintains the vortex, the storm's visible size can decrease. The Great Red Spot may also lose energy by mixing with surrounding air of different properties. The storm's interior can differ in temperature, cloud composition, and haze content compared with its surroundings. The boundary is where these differences meet. If the boundary becomes more permeable due to turbulence, mixing increases. Mixing can dilute the storm's distinct color and can blur the boundary. It can also reduce the contrast that makes the storm's outline easy to measure. In some cases, a storm might appear smaller because its edges become less distinct, even if the deeper circulation remains. In other cases, the mixing is physical, meaning the vortex truly loses coherent structure near the edges. Both can happen, and the neighborhood dynamics influence both. Observations show that the Great Red Spot sometimes sheds reddish flakes or fragments, small pieces that separate and drift away. These fragments can be traced for a time as they move along nearby jets, gradually fading as they mix. This process can be thought of as the storm losing skin. The interior vortex persists, but its outermost layers are stripped. If this stripping happens repeatedly, the storm's visible perimeter retreats inward. The storm becomes more compact. It can also become more circular because the outer stretched regions are more vulnerable to being torn away by shear and interactions. The ends of an elongated oval can be especially exposed to strong flow, and therefore may shrink faster than the sides, leading to a rounder shape. The neighborhood also includes other long-lived features that can compete with the Great Red Spot for space and energy. Jupiter sometimes hosts other large ovals in nearby latitudes. These ovals can form through mergers of smaller storms and can persist for years. Their presence can change the local flow field and can influence how many smaller vortices survive to reach the Great Red Spot. If the surrounding region becomes more turbulent, it can increase the frequency of interactions. If it becomes more stable, interactions might be less frequent. Therefore, the storm's shrinkage could be tied not only to its internal properties, but to shifts in the broader storm population near its latitude. One of the key insights from modern observations is that the Great Red Spot is not simply shrinking because it is being starved of storms. It is shrinking while still showing strong circulation and while still interacting with a lively surrounding atmosphere. This suggests a slow evolution in how the vortex exchanges energy with its environment. The exchange might be less favorable to maintaining a large footprint, perhaps because the jets and turbulence strip the outer layers more efficiently than before, or because the storm's internal structure changes in a way that makes it less able to resist erosion. The exact balance remains uncertain, but the neighborhood dynamics provide plausible mechanisms grounded in fluid behavior. Uncertainty remains because each interaction is complex and because observations are intermittent. Jupiter is observed intensively during certain campaigns and less intensively at other times. Smaller vortices evolve quickly and can be missed between observations. When an interaction is captured, it provides a clear example of how the boundary can be disturbed and how filaments can be shed. Yet a complete accounting of how often these events occur and how much they contribute to long-term shrinkage is difficult. Observations indicate that edge shedding and interactions are real, but it remains uncertain how much of the long-term trend is driven by discrete encounters versus continuous shear and turbulence. This neighborhood layer leads naturally to the next inward step energy supply. A vortex that loses material at its edges can persist if it receives energy from the surrounding flow or from deeper convection. Jupiter has internal heat, and that heat drives upward motion that can energize storms. The question then becomes how the Great Red Spot is powered over long time, and how changes in energy flow could allow a storm to persist while its visible size decreases. The next region, therefore, moves from the storm's neighborhood interactions to Jupiter's broader energy and heat flow, tracing the source of motion that keeps long-lived storms alive. A long-lived storm must be powered, even on a planet with low friction. The Great Red Spot persists for centuries, which implies that its circulation is maintained against the slow drain of turbulence and radiative cooling. On Jupiter, the power source is not only sunlight, it is also internal heat, rising from the planet's deep interior. This heat drives convection, and convection provides a background supply of motion that can feed storms. The shrinking of the Great Red Spot therefore cannot be understood as a simple running down of a single isolated whirl. It must be seen as an evolving balance between energy supply and energy loss in a deep, rotating atmosphere. Jupiter receives sunlight, and the upper clouds reflect a significant fraction of it. The sunlight warms the upper atmosphere and helps set temperature gradients that can drive weather. Yet Jupiter's distance from the Sun means that sunlight is weaker there than near Earth. Even so, Jupiter is not quiet. Measurements show that Jupiter emits more energy than it receives from the Sun. The extra energy comes from its interior, released slowly over time. Jupiter continues to cool and contract very gradually, and this slow change releases heat. The interior heat emerges upward, passing through the deep layers of hydrogen and helium and into the atmosphere. This is a steady input that can maintain vigorous convection on a global scale. Convection is the rising of warm material and the sinking of cooler material. In Jupiter's atmosphere, convection can occur in deep columns where warm gas rises, expands, cools, and forms clouds as certain compounds condense. In the visible cloud layers, convection appears as bright plumes and as storm systems that rise and spread. These convective events can be localized and intense. They can also be part of broader patterns where zones tend to have more rising motion and belts tend to have more sinking motion. The vertical motion associated with convection is one of the ways energy is transported upward from the interior and redistributed by winds. A vortex like the Great Red Spot can draw energy from its surroundings in several ways. One way is through interactions with jet streams. The storm sits in a shear environment where winds flow past in opposite directions on either side. Under certain conditions, a vortex can extract energy from this shear, maintaining its rotation. Another way is through the merging of smaller vortices, which can add circulation. A third way is through coupling with deeper convection, where vertical motions below can replenish the vortex's structure and maintain its temperature and pressure differences. The relative importance of these pathways remains uncertain, but the existence of multiple pathways helps explain why the storm can persist, even while its visible outline changes. Energy loss occurs primarily through turbulence and through radiation. Turbulence breaks organized motion into smaller eddies, and at small scales this motion dissipates into heat. Radiation allows the atmosphere to cool by emitting infrared energy to space. The Great Red Spot is part of a system where energy is continually moved, transformed, and lost. If energy input and energy loss balance, the vortex can remain stable. If energy loss exceeds input, the vortex can weaken and shrink. If energy input exceeds loss, the vortex could grow or become more vigorous. Shrinking suggests that the balance at the cloud top footprint may shift toward loss, or that the vortex may be reorganizing into a tighter form that reduces its exposed perimeter where loss occurs. The storm's exposed perimeter matters because many losses occur at the boundary. The boundary is where shear and turbulence are strongest, where filaments are shed, and where mixing dilutes coherent structure. A larger storm has a longer boundary, and therefore more area where turbulence can develop. If the storm becomes smaller, the boundary length decreases, which can reduce the total rate of energy loss through boundary mixing. In this way, a shrinking vortex can be a stable outcome. The storm becomes more compact and reduces the surface through which it leaks energy, allowing it to persist at a smaller size. This is not a guarantee. It is a plausible mechanism consistent with fluid behavior, where a system adjusts to reduce loss when supply is limited. The energy supply from Jupiter's interior also varies with depth and with location. The global average heat flow is steady, but local convective events can be intermittent. The Great Red Spot may receive energy from deep motions that are not constant in time. If the pattern of convection beneath the storm changes, the storm's supply could vary. A reduction in supply could allow the storm to lose outer layers more quickly than it can replenish them, leading to shrinkage. Alternatively, supply could remain similar while the storm's environment becomes more erosive, still producing shrinkage. These possibilities show that shrinkage does not require a dramatic change in Jupiter's global heat. It can arise from changes in local coupling between the vortex and its surroundings. Jupiter's internal heat also drives a broad circulation that interacts with rotation. Rising heat does not produce simple vertical motion only. The planet's fast rotation organizes convection into patterns and feeds jet streams. The jets themselves may be maintained in part by convective driving that pumps momentum into large-scale flows. If the jets change in strength or position over time, the Great Red Spot's confinement corridor changes. This changes how the storm exchanges energy with the background flow. Therefore, heat flow and storm shrinkage can be linked indirectly through the evolution of jets and belts. In addition, Jupiter's atmosphere contains latent heat from cloud formation. When a gas condenses into a cloud, it releases heat. This latent heat can add buoyancy and strengthen convective updrafts. In Jupiter's deep atmosphere, water is expected to be an important condensing substance, because water condensation occurs at deeper, warmer levels and can involve large energy release. Strong water-driven convection can produce powerful storms and influence the dynamics of belts and zones. The Great Red Spot sits above these deeper layers, and if it couples to deep convection, latent heat processes could matter to its long-term maintenance. The details of this coupling remain uncertain, but it provides another plausible channel for energy exchange. Energy considerations also help explain why the Great Red Spot can remain strong while shrinking. If the storm's core remains energetic, its maximum wind speeds can remain high. A strong core can persist even if the outer layers are eroded. The storm's visible size may shrink because the outermost cloud features that define its boundary are stripped away, while the deeper circulation and core vorticity remain. Over time, the storm could evolve toward a smaller, more stable configuration that is easier to sustain with the available energy supply. This would be consistent with a vortex adjusting to its environment rather than fading away rapidly. Yet energy balance alone does not define the full story. because a storm's structure is three-dimensional. Energy supply and loss vary with altitude. The cloud-top layers cool efficiently by radiation. Deeper layers cool less efficiently to space and can store heat and momentum. A deep vortex can therefore act as a reservoir, buffering the storm against short-term changes at the top. If the Great Red Spot extends deep, it may remain stable even as the cloud-top expression shrinks. If it is shallow, it may respond more quickly to changes in cloud-top turbulence and radiation. This points toward the next inward step, the vertical structure beneath the visible clouds, and how the storm's depth and layering influence what shrinking at the top really means. Uncertainty remains about the exact partition of energy sources. Observations indicate that Jupiter's internal heat is significant, and that storms can be sustained by a combination of internal heat-driven convection, jet shear, and vortex interactions. It remains uncertain exactly how much energy the Great Red Spot draws from each pathway, and how that balance changes over decades. It remains uncertain whether the shrinking trend is driven primarily by reduced energy input, increased boundary erosion, or a reorganization that reduces losses. The next step in the inward path moves beneath the cloud tops to the atmospheric layers below, where the storm's depth and vertical structure become central to interpreting what is really happening. Below Jupiter's visible cloud tops, the atmosphere continues downward in a long gradient of pressure, temperature, and density. The bright bands and the Great Red Spot are drawn in the upper layers, where sunlight is reflected and where certain gases condense into clouds. Yet these upper clouds are only a thin skin compared with the full depth of Jupiter's atmosphere. The planet has no solid surface to stop circulation. Instead, gas becomes steadily denser until it behaves more like a liquid, and then it continues into deeper regions where hydrogen changes its physical behavior under immense pressure. In this setting, the most important question behind the shrinking story is whether the Great Red Spot is mainly a shallow cloud-top whirl or a deep vortex rooted far below the visible layers. The visible cloud decks are associated with condensation. At different depths, different compounds condense as temperature and pressure reach the right conditions. Higher in the atmosphere, ammonia can condense, forming cloud particles that reflect sunlight and contribute to Jupiter's pale appearance. Deeper down, ammonium hydrosulfide can form another cloud layer. Deeper still, water clouds are expected because water condenses at warmer temperatures and higher pressures. These layers are not perfectly uniform sheets. They are shaped by vertical motion. Where air rises, it cools, and condensation can thicken clouds. Where air sinks, it warms, and clouds can thin or evaporate, revealing deeper, darker layers. The belts and zones seen from above are tied to these vertical patterns, which can extend deeper than the visible clouds. The Great Red Spot sits within this layered atmosphere and likely affects multiple levels at once. At the cloud top, the storm's boundary is traced by rapid winds and by swirling textures. Beneath that, the vortex can extend into regions where clouds are different, and where visibility and reflected sunlight is reduced. In these deeper layers, the storm may still be present as a pressure and wind structure, even if it cannot be seen directly as a red oval. A storm can be deep without being equally visible at every level, because the tracers used to see it change with chemistry and with lighting. As pressure increases downward, the atmosphere becomes denser and motion becomes more massive. A flow in the deeper atmosphere involves more material than a flow at the top. This matters for longevity. A deep vortex contains more mass and therefore more momentum. Momentum is harder to change quickly. This can make a deep vortex more stable against short-term disturbances at the cloud tops. If the Great Red Spot extends deep, It can persist as a coherent circulation even while the upper visible layers are sculpted by shear and turbulence. The cloud top outline could shrink while the deeper core remains strong, because the visible boundary is where filaments are stripped and where haze patterns define the measured size. The vertical temperature structure of Jupiter's atmosphere also influences how storms behave. In the uppermost layers, temperatures are low and radiation to space is efficient, so the atmosphere can cool readily. Deeper down, temperatures rise and radiative cooling becomes less direct, because the atmosphere becomes optically thicker and heat is transported more by convection and by mixing than by direct radiation to space. A deep vortex lives partly in this convective environment, where heat flows upward from the interior. A shallow vortex lives more in the radiatively cooled layers, where energy can leak to space more directly. The balance between these regimes affects how a storm maintains itself. Jupiter's rapid rotation organizes motion throughout much of the atmosphere, but rotation interacts with depth. At some level, jets and vortices are strongly expressed in the visible cloud layers. Whether these jets persist with similar strength far below depends on the planet's internal structure and on how momentum is transported downward. Observations and models suggest that at least some jet structure extends below the visible clouds, though the details vary with depth and latitude. If the jets that confine the Great Red Spot are deep, then the confinement corridor exists not only at the top but through a thicker vertical column. This would provide a more stable container for the storm. If the jets are shallow, then the confinement is mainly a surface effect, and the deeper flow could be less organized, potentially allowing the vortex to interact differently with its surroundings. There is also the question of how the storm's shape changes with depth. A vortex can be wider at one level and narrower at another. It can have a cap-like structure where the visible top is broad. While the deeper portion narrows, it can also have the opposite, where a deep, thick core supports a broad top. The visible shrinking could therefore reflect changes in the upper cap rather than in the deeper column. If erosion and mixing at the cloud tops remove the outer layers, the top could become smaller while the deeper vortex remains similar. This would appear as shrinking in images even if the storm's deeper extent remains stable. The chemistry and haze structure within the storm also depends on vertical motion. The Great Red Spot's red color is thought to arise from complex particles or molecules produced when certain materials are exposed to sunlight and energetic conditions. For such material to remain visible, it must be present at high altitude where sunlight can process it and where it can remain suspended. A strong vortex can lift material upward and maintain a high-altitude haze layer. If the storm's vertical circulation changes, the haze altitude and thickness can change, altering color and contrast. A storm could look smaller if the region of high-altitude colored haze contracts, even if the deeper circulation remains. Conversely, a storm could look redder if the haze is concentrated in a smaller area and lifted higher. These appearance changes are part of why shrinking must be interpreted with depth in mind. The deeper atmosphere also carries the bulk of water vapor and the strongest latent heat potential. Water condensation releases a large amount of heat compared with condensation of lighter compounds at colder altitudes. When water condenses in deep convective storms, it can drive powerful updrafts and influence the energy budget of the atmosphere. If the Great Red Spot interacts with deep layers where water weather is active, it may draw energy from deep convection in ways that are not obvious at the cloud tops. It might be connected to a deeper convective regime that sustains its rotation, even while the upper outline is eroded by shear. In addition, Jupiter's atmosphere becomes electrically conducting at great depth as pressure rises and hydrogen transitions into a state where electrons move more freely. In these deeper regions, magnetic forces can influence flow. The exact depth where this becomes important depends on pressure and temperature, and the details remain an area of active research. The Great Red Spot likely does not extend into the deepest conducting regions in a way that is directly measured at present, but the existence of a conducting interior provides a conceptual inner boundary for atmospheric motion. At some depth, flow patterns may couple to magnetic effects and to the planet's internal dynamics. This sets a limit on how deep purely atmospheric vortices can extend in their familiar form. The most important practical implication of these layers is that the Great Red Spot can change at the top without being close to disappearing. The visible shrinking is a change in the storm's cloud top footprint, defined by the patterns of clouds and hazes that mark its circulation in reflected sunlight. The deeper storm, if it exists, is defined by pressure anomalies, wind fields, and mass distribution in thicker layers that are not directly seen by ordinary imaging. The upper layers are where turbulence strips filaments and where jets shear the boundary. These are the layers most exposed to erosion. The deeper layers are where the storm may store momentum and maintain a more stable core. Shrinking at the top can therefore be a surface expression of a deeper structure adjusting, tightening, or losing its outermost shell. This layered perspective also clarifies why modern measurements that probe depth are so important to the shrinking story. Cloud-top images provide a clear record of the shrinking footprint. The deeper layers determine whether the storm is fundamentally weakening or whether it is reorganizing into a smaller, still robust configuration. Without depth information, the interpretation would remain ambiguous. With depth information, the shrinking can be placed into a three-dimensional context. At this stage of the inward path, the picture is a descent through layers visible clouds, deeper cloud decks, convective regions where heat rises and water condenses, and still deeper zones where the atmosphere becomes denser and the interior begins to influence flow in different ways. The Great Red Spot sits within this layered world. Its visible outline is only one cross-section through a deeper circulation. Shrinking, at the cloud top, is therefore a real change, but not necessarily a complete measure of what the storm is doing in depth. The next inward step moves from layered structure to appearance and chemistry, because the storm's changing color and contrast are closely tied to altitude, mixing, and haze production. In that region, the red hue becomes a diagnostic of what the storm is lifting and how the upper layers are changing as the visible footprint contracts. The Great Red Spot's color is one of its most striking features, yet it is also one of the most informative. A storm's color on Jupiter is not paint. It is the outcome of chemistry, particle size, haze altitude, and the way sunlight interacts with cloud layers. When the Great Red Spot changes color, it suggests changes in what is being lifted, where it is being lifted to, and how long it remains exposed to sunlight and radiation. When the storm shrinks, its color changes can become part of the explanation, because a smaller storm may have a different balance of mixing and vertical circulation than a larger one. Appearance becomes a clue to process, not a decoration. The basic palette of Jupiter comes from ammonia clouds, deeper cloud layers, and haze particles. Ammonia clouds are generally pale. Belts can appear darker because clouds are thinner or because deeper. Darker material is visible. Hazes can tint regions yellowish or brownish. The Great Red Spot often appears red-orange, which implies an additional component. Many studies suggest that the reddish color is produced by complex molecules or particles formed when certain gases or aerosols are altered by sunlight in the upper atmosphere. This process can be described as photochemistry, chemical reactions driven by light. Ultraviolet radiation and energetic particles can break molecules apart and allow new compounds to form. The resulting particles can absorb blue light more than red light, making the region appear reddish. For photochemistry to produce visible red material, the material must be present at relatively high altitude where sunlight and ultraviolet radiation can reach it. This connects color to vertical motion. A strong vortex can lift material upward from deeper layers and keep it aloft. It can also trap material within its circulation, allowing it to be processed over time. The Great Red Spot is an anticyclone with a stable circulation that can isolate its interior from surrounding air. This isolation can create a laboratory where haze particles form and persist. If the vortex changes in strength or in vertical extent, the altitude and density of haze can change, altering color. Color also depends on particle size. Small particles scatter light differently from larger particles. A haze made of very small particles can appear differently from a haze made of larger aggregates. The Great Red Spot's color may deepen when the haze particles become more abundant, more strongly absorbing, or more concentrated in the uppermost layers. It may pale when particles settle, when mixing with surrounding air dilutes the haze, or when the chemical production of chromophores, the color-bearing compounds, slows. The term chromophore is used for a substance that absorbs certain wavelengths strongly and therefore produces color. In Jupiter's atmosphere, the exact identity of the chromophore remains uncertain, though plausible candidates exist in laboratory and modeling work. Observations indicate a chemical origin, but it remains uncertain which specific compounds dominate. The Great Red Spot's color changes can occur on timescales shorter than the shrinking trend. There have been periods when the spot appears notably deeper red than usual, and other periods when it appears paler. These changes can be influenced by changes in the surrounding atmosphere as well. If the belts around the spot become darker, the contrast can change, making the spot appear different even if its intrinsic hue remains similar. Therefore, color must be assessed with calibrated measurements rather than by casual viewing. Still, the repeated observation of a deepening and paling suggests real changes in haze and chemistry. The link between color and shrinking can be approached through mixing and boundary behavior. A larger storm has a larger perimeter where mixing can occur. If the boundary is turbulent, mixing can draw in surrounding air and carry out interior air. This mixing can dilute the haze concentration that produces the red color. If the storm becomes smaller and more compact, and if its boundary becomes sharper and more stable, it could reduce mixing and allow haze to remain concentrated, deepening the color. Conversely, if shrinking is accompanied by increased boundary turbulence and filament shedding, it could enhance mixing and strip colored material away, leading to paling. Both behaviors are possible, and the observed color record suggests that the balance can change over time. Vertical circulation is another pathway. If the Great Red Spot's upwelling becomes stronger in a smaller footprint, it could lift material higher and create a thicker haze layer in a more concentrated region, producing a deeper red. If upwelling weakens, the haze could thin and the color could fade. Temperature measurements of the storm's top can provide clues, because higher cloud tops tend to be colder. A colder top can indicate that the visible clouds are higher, which could be consistent with stronger vertical lift. Yet temperature patterns also depend on radiation and on surrounding atmospheric conditions. Therefore, temperature is a clue, not a direct measurement of vertical velocity. The chemistry of the Great Red Spot also depends on the availability of precursor compounds. Precursor compounds may include ammonia and other molecules present in Jupiter's upper atmosphere, as well as more complex compounds that can be brought up from deeper levels. If the storm's circulation changes its connectivity to deeper layers, the supply of precursors can change. A storm that becomes more isolated from below might have fewer fresh precursors, leading to slower haze production. A storm that remains well connected could continue to feed the photochemical factory at its top. The connection between deep supply and surface color is plausible, but it remains uncertain in detail because deep composition is difficult to measure directly at the storm's location. Color is also influenced by sunlight exposure, which changes with Jupiter's seasons and with the storm's own vertical profile. Jupiter's axial tilt is small compared with Earth's, so seasonal changes are modest, yet they still exist. The intensity of sunlight at a given latitude can vary, and the background haze can vary with solar activity. Solar ultraviolet output changes with the solar cycle. These factors can influence photochemistry rates. The great red spot's color may therefore respond not only to internal dynamics, but to changes in external forcing. However, the main energy of Jupiter's atmosphere comes from internal heat, so sunlight variations are only part of the story. When the great red spot shrinks, its color can also change due to geometric effects in imaging. A smaller region can appear more saturated if it contains a concentrated haze. It can also appear less saturated if it becomes mixed with surrounding material. Color gradients across the storm can shift. The central region can appear different from the outer ring. The outer ring often contains strong shear and filament structures. If the outer ring becomes thinner or is stripped away, the remaining storm may show a different average color because the surviving region has a different haze distribution. Shrinking can therefore change the measured color by changing which parts of the vortex remain visible in the outline. In calm scientific terms, the most careful statement is that observations indicate the great red spot's color varies over time, and that these variations are tied to haze chemistry and vertical mixing. It remains uncertain which exact compounds produce the color, and how changes in vortex dynamics and depth translate into changes in haze production and retention. The shrinking trend is clear in size measurements, and color changes sometimes accompany periods of structural change. But the relationship is not a simple one-to-one link. The red color is best treated as a diagnostic, one piece of evidence among several, rather than as a direct measure of storm strength or size. This layer of appearance and chemistry also points toward the next inward region's stability and shape. A vortex confined by jets can change its aspect ratio and become more circular as it adjusts to shear. The storm's geometry is not arbitrary. It reflects the balance between internal rotation, external shear, and vertical structure. Understanding why the great red spot's shape becomes more compact is a step toward understanding why its footprint shrinks while it persists. The next section therefore moves from color as a clue to shape as a physics outcome, examining the storm's stability and the reasons a vortex can tighten into a smaller, rounder form under Jupiter's atmospheric conditions. The great red spot's shape is the visible outline of a balance. Inside the vortex, air rotates in a coherent circulation. Outside it, fast jets stream past in opposite directions. Between them, shear stretches and compresses. A long-lived vortex must find a form that is stable within this environment. When the great red spot becomes smaller and more rounded, it is not simply changing in appearance. It is expressing a change in stability conditions, a shift toward a geometry that the surrounding flow can maintain. Shape becomes a physical outcome of forces and flows. On a rotating planet, vortices tend to organize into coherent structures because rotation discourages random mixing at the larger scales. Yet vortices are still deformed by shear. If the surrounding flow pulls more strongly on one side than the other, the vortex can elongate. If the surrounding flow squeezes it, it can become more compact. The Great Red Spot historically appears as a large oval with a strong east-west elongation. Its latitude band is defined by jets that flow east-west, so elongation in that direction is natural. The vortex sits in a corridor of shear aligned with the planet's rotation. The corridor tends to stretch features along the direction of flow. As the storm shrinks, its aspect ratio can change. A smaller vortex can resist deformation differently than a larger one because its boundary interacts with shear over a shorter length. A long elongated vortex has extended ends that protrude into different parts of the background flow and are therefore exposed to stronger differential stress. Those ends can be stripped more easily, especially when nearby turbulence and smaller vortices pass by. If the ends are repeatedly eroded, the vortex naturally becomes less elongated. It approaches a more rounded form because the most vulnerable stretched regions are removed first. This is a simple geometric explanation for why a long storm can become more compact without requiring the entire vortex to weaken uniformly. The boundary of the Great Red Spot is also a place where instabilities can form. When a fast flow passes a vortex, the boundary can develop waves and rolls. These can peel off as filaments. In fluid dynamics, shear boundaries can be unstable, producing structures that mix and dissipate energy. A larger vortex has a longer boundary and therefore more opportunity for such instabilities to grow. If energy supply is limited or if erosion is strong, the boundary may retreat inward, reducing the total boundary length and making it easier for the remaining vortex to maintain coherence. In this way, becoming smaller can be a stability strategy in a physical sense. The system evolves toward a configuration where loss processes are reduced. A vortex can also change shape if the confinement corridor changes. The jets above and below the Great Red Spot can shift slightly in speed and position. If the jets become closer together, the available latitude space decreases, and the vortex may be squeezed. If the jets change in relative speed, the shear profile changes, altering the balance of stretching and compression. Even small changes in the background flow can produce noticeable changes in the shape of a large vortex. Jupiter's belts and zones vary on timescales of years, and the jet structure can show subtle changes. The Great Red Spot's shape variations can therefore reflect both internal reorganization and changes in the external corridor. The vortex's internal structure also influences shape. A vortex is not uniform from center to edge. The winds are often strongest near the periphery, where velocity gradients are steep. The interior can have slower rotation and can contain different cloud textures. If the distribution of vorticity changes, the vortex can tighten. A tightening vortex concentrates rotation nearer the center. This can allow the boundary winds to remain strong even as the radius decreases. Such a change can make the vortex more resistant to being pulled apart by external shear because the core becomes more dominant relative to the outer layers. The visible result is a smaller, more coherent oval with a sharper boundary. Vertical structure matters here as well. A deep vortex interacts with surrounding flow at multiple levels. If the vortex is deep, it can be more stable because its rotation is supported by a thick column of moving fluid. A shallow vortex is more easily deformed because it exists mainly in a thin layer. If the Great Red Spot's depth remains large while the top shrinks, the vertical column may become relatively thicker compared with its horizontal size. This thickening in relative terms can also increase stability, allowing the storm to persist as a compact vortex rather than as a broad oval. The idea resembles a spinning column that is narrower but still tall, maintaining coherence because its depth provides inertia. The Great Red Spot's shape also responds to interactions with nearby vortices. When a smaller vortex merges into it, The boundary can distort temporarily. When a smaller vortex grazes it, the boundary can be pulled outward or inward, creating lobes. Over time, repeated interactions can round the outline by stripping protrusions and smoothing the perimeter. The vortex can lose irregular edges through mixing. The result is a more regular shape. This smoothing is not necessarily a sign of weakening. It can be a sign that the vortex has shed unstable features and settled into a shape that is easier to maintain. Observations show that the Great Red Spot sometimes appears to develop a more circular form than its historical oval. This is consistent with the idea that the long axis has reduced more than the short axis. It is also consistent with the idea that the vortex is becoming more compact under continued shear and erosion. The reduction in visible area can be accompanied by sharper boundary definition in some periods, suggesting that while the overall footprint decreases, the remaining vortex can remain well organized. Shape and stability are also linked to waves and large-scale patterns in Jupiter's atmosphere. The belts and zones support wave activity that can modulate jet strength and can perturb vortices. If wave patterns change, the deformation forces on the Great Red Spot can change. The storm can respond by adjusting its shape. A stable vortex under changing external forcing can exhibit slow oscillations in aspect ratio and boundary curvature, much like a slowly breathing shape. The shrinking trend is the long-term drift of these oscillations toward a smaller mean size. In this physical picture, shrinking does not require a sudden loss of energy. It can occur through the preferential erosion of vulnerable parts, through boundary instability shedding, through shifts in confinement, and through internal tightening of the vortex's vorticity distribution. These processes can operate simultaneously. They produce a storm that remains persistent but evolves in geometry. The storm's change becomes a statement about how long-lived vortices behave in a sheared, rotating, stratified atmosphere. Uncertainty remains about which process dominates at any given time. Observations indicate boundary shedding and interaction events. They also indicate changes in shape over years. It remains uncertain how much of the shape change is driven by changes in the surrounding jets versus internal reorganization. It remains uncertain how the depth structure evolves as the footprint shrinks. These uncertainties are bounded by what can be measured cloud-top wind profiles, thermal patterns, and, from spacecraft, depth-related signals. With the shape stability balance described, the inward path moves to the specific mechanisms by which the storm loses material and energy at its edges. Filament shedding and turbulent mixing are not just visible details. They are the practical pathways for erosion that can reduce size while leaving a core intact. The next section follows these edge loss processes closely, showing how a vortex can persist for centuries while slowly shedding its outer layers. The Great Red Spot changes most visibly at its edges. The center remains a relatively stable core of rotation, while the boundary is a zone of shear, turbulence, and exchange with the surrounding atmosphere. This boundary is where the storm can lose material and lose energy, and it is where shrinking can occur without the storm disappearing. The process is often quiet in the sense that it does not involve a sudden collapse. It involves the gradual peeling away of outer layers, carried off by nearby jets and mixed into the belts. The storm persists as a coherent vortex while its footprint retreats inward. One edge loss process is filament shedding. The boundary of the Great Red Spot can stretch into long streamers that curl away from the oval. These streamers can be reddish because they contain the same haze and cloud material that gives the storm its color. Once they detach or thin enough, they're carried away by surrounding winds. They can extend into nearby belts, forming streaks that later break up and fade as they mix. Each filament represents a small loss of the storm's outer material, a transfer from the vortex into the wider atmospheric flow. Filaments form because the boundary is not a solid wall, it is a moving interface. The storm's outermost layers rotate, and adjacent winds flow past in different directions and speeds. The resulting shear can pull on the outer layers, stretching them outward. If a stretched layer remains connected, it appears as a streamer. If the connection weakens through turbulence, the streamer separates. This is a common behavior in fluids where a rotating region meets a fast-moving background. The interface generates long, thin features that carry vorticity and traces away from the main vortex. The Great Red Spot also has an outer ring where winds can be especially strong. This ring can act as a barrier that helps isolate the interior. Yet the ring is also where small instabilities can grow. Small waves along the boundary can amplify, creating scalloped edges and small rolls that evolve into filaments. When these features detach, they remove pieces of the boundary ring. If the ring is thinned repeatedly, the remaining coherent boundary moves inward. The storm's measured size decreases. The core remains, but the perimeter retreats. Another edge loss mechanism is turbulent mixing. Mixing occurs when the boundary becomes permeable and surrounding air is stirred into the vortex while vortex air is stirred out. Mixing can be driven by shear instabilities, by nearby vortices passing close, and by wave activity in the jets. Mixing blurs the sharpness of the boundary and changes the composition of the outer layers. It can dilute the haze that produces the red color and can alter cloud patterns that define the storm's outline. If the boundary becomes less distinct, the storm can appear smaller in images because the contrast that defines the edge decreases. If mixing is strong enough, it can also weaken the vortex by reducing the coherence of its outer rotation. Edge erosion can also involve the interaction with smaller vortices that graze the Great Red Spot. When a smaller storm passes near, it can tug at the boundary, pulling out a filament or creating a protrusion that later breaks off. Even if the smaller vortex does not merge, it can disturb the boundary ring and increase turbulence. Over time, repeated grazing encounters can accelerate erosion. This mechanism is episodic. It occurs in events rather than continuously. Yet a series of such events over years can contribute to the long-term shrinking trend. There is also the idea of vorticity loss. Vorticity is the measure of rotation in a fluid. A vortex persists because it contains vorticity concentrated in a coherent region. Vorticity can be redistributed and diffused by turbulence. When filaments peel off, they can carry vorticity away from the main core. When mixing occurs, the vorticity distribution becomes more spread out and less intense at the boundary. A vortex can shrink when vorticity is lost from the outer region faster than it is replenished. The core may remain strong, but the outer vorticity weakens, allowing the boundary to contract. This can produce a smaller vortex with stronger relative winds near its new boundary, depending on how the remaining vorticity is distributed. Replenishment is the other side of the balance. The Great Red Spot can gain vorticity and energy from the surrounding flow. Merging with other anticyclones can add rotation. Interaction with shear can transfer energy into the vortex under certain conditions. Deep convection could, in principle, supply energy and maintain the storm's structure. Shrinking suggests that replenishment may be sufficient to maintain a core, but insufficient to maintain a large outer footprint against ongoing erosion. The storm survives, but in a smaller form. This is consistent with the idea that the storm is adjusting toward a configuration that balances supply and loss at a reduced size. Edge erosion also relates to the storm's wake, downstream of the Great Red Spot. The diverted jets create a region where turbulence can be strong. This wake can draw material from the storm and stretch it into long patterns. The wake is also a region where new small vortices can form from shear and instability. These vortices can then interact again with the storm. The wake is therefore part of a feedback loop. The storm modifies the flow. The modified flow produces turbulence and vortices. Those features then interact with the storm, influencing its boundary. This loop can maintain a constant level of edge activity even while the storm's overall size changes slowly. The quietness of this process can be misleading. Filament shedding can look dramatic in time-lapse images because long red streamers appear and curl away. Yet the total mass and energy involved in any single streamer may be small compared with the storm's full circulation. The storm is enormous. A streamer is a small fraction of its outer layer. The significance is not that one streamer weakens the storm, but that many such events over time can produce cumulative change. Shrinking is a long story of repeated small losses. Observations indicate that the Great Red Spot's perimeter has become more compact over time, and that edge-shedding events are part of its behavior. It remains uncertain how the frequency and intensity of these events change with broader atmospheric cycles. It remains uncertain whether changes in the surrounding jets over decades alter the erosion rate. It remains uncertain how deep the erosion penetrates, meaning whether the storm loses only its uppermost layers or whether deeper vorticity is also reduced. These uncertainties are addressed by looking inward to depth measurements and by comparing observations across wavelengths and instruments. This edge-lost layer is the bridge between what is seen and what must be inferred. The visible shrinking is the contraction of the cloud-top footprint, and edge erosion provides a physically plausible route to that contraction. The vortex sheds filaments, mixes at its boundary, and loses outer vorticity. It remains coherent because its core persists, and because some replenishment continues. The result is a storm that changes slowly rather than ends abruptly. The inward path now moves to the deeper question of how far down the Great Red Spot extends, and how deep structure influences its longevity. Depth is not directly visible in ordinary imaging, so this region must hold evidence and uncertainty together. It will describe what is known from spacecraft measurements, and what remains uncertain about the storm's deep anchor as the cloud-top footprint contracts. Depth is the quiet part of the Great Red Spot story. The shrinking is measured at the cloud tops, where the storm's outline is drawn in reflected sunlight. Depth is inferred because the layers below are hidden from direct view by clouds and by the gradual thickening of the atmosphere. Yet depth matters because it determines how much mass and momentum are involved in the vortex, and how strongly it can resist the shearing and erosion that operate at the top. A shallow storm is more like a surface whirl. A deep storm is more like a rotating column embedded in a thick fluid. The difference changes how shrinking should be interpreted. A deep vortex contains more material in motion. As pressure increases downward, the density of the atmosphere increases. A given volume of air at depth holds more mass than the same volume near the cloud tops. If the vortex extends into these denser layers, it carries more angular momentum, the conserved quantity associated with rotation. Angular momentum is difficult to change quickly. This can make a deep vortex stable over long time even when its upper boundary is disturbed. It can maintain a coherent core while losing and regaining cloud-top traces. In this way, depth offers a pathway for survival. During shrinking, the storm's visible top can contract, while the deeper circulation remains robust. A shallow vortex, by contrast, is more exposed. Its circulation is concentrated in low-density upper layers where radiative cooling is efficient and where turbulence at boundaries can more easily redistribute vorticity. If the Great Red Spot were shallow, The observed loss of area might be more directly tied to a loss of total circulation strength. The storm could be fading in a fundamental sense. The difference between these interpretations is one reason depth becomes central to what is really happening. Depth is difficult to measure because a vortex is not a solid object, and because Jupiter's atmosphere has no clear lower boundary. Yet there are indirect ways to probe depth. One method uses thermal structure. If the storm's top is higher than surrounding clouds, it can be colder. If it is deeper, it can influence temperature patterns at different altitudes. Infrared observations can map temperatures and show anomalies associated with the storm. These temperature maps suggest that the Great Red Spot has a distinct thermal signature, consistent with a large-scale circulation that affects more than one cloud level. However, thermal signatures do not alone provide a depth in kilometers, because temperature is influenced by radiation and by horizontal advection, as well as by vertical motion. Another method uses microwave observation. Microwaves can penetrate deeper into Jupiter's atmosphere than visible light, because they are less strongly scattered by the upper clouds. The brightness at microwave wavelengths depends on the presence of certain gases, especially ammonia, which absorbs microwaves. Where ammonia is abundant, microwave emission from deeper warm layers is absorbed more strongly, producing a different signal than where ammonia is depleted. A microwave map can therefore reveal patterns of composition and temperature at depths below the visible clouds. If the Great Red Spot alters ammonia distribution and vertical mixing, it can leave a microwave imprint that indicates a deep structure influencing gas at depth. Such measurements suggest that the storm is not confined to the very topmost layer, because its influence is seen in deeper composition patterns. A further method uses gravity. A deep storm involves a large mass of moving gas. Even though the gas is not a solid mountain, it contributes mass distribution that can slightly alter the gravitational field in the region. A spacecraft flying over the storm can detect tiny changes in gravity through changes in its motion. If a consistent gravity anomaly is detected associated with the Great Red Spot, it implies that the storm extends deep enough and contains enough mass anomaly relative to the surroundings to affect gravity measurably. This is a powerful approach because gravity responds to mass directly rather than to cloud traces. A gravity signal implies a deep and massive structure, because a shallow layer at low density would not contribute much mass. These depth probes lead to a broad picture that the Great Red Spot is deeper than a thin cloud-top feature. The storm appears to extend downward through a substantial fraction of Jupiter's weather layer. In general terms, the inferred depth is often described as hundreds of kilometers, indicating that the vortex reaches far below the visible cloud tops. This depth is large compared with Earth's troposphere thickness, and small compared with Jupiter's full radius, placing the storm in a significant atmospheric shell, where pressure and density change strongly with depth. The exact depth remains uncertain because measurements must be interpreted through models that connect observed signals to vertical structure. Yet the existence of depth itself is supported by multiple lines of evidence. Uncertainty remains about how the storm's depth changes over time. The shrinking trend is measured in the storm's cloud-top footprint. A deep storm could shrink at the top while maintaining its deep extent, or it could shrink in both horizontal area and vertical penetration. Depth measurements have limited temporal coverage because they rely on specific spacecraft flybys and particular observational campaigns. Therefore, it remains uncertain whether the deep structure is stable, slowly changing or changing in step with the visible shrinkage. There is also uncertainty about geometry at depth. A vortex can have a different shape below than above. It can be broader near the cloud tops and narrower below, or it can be thick and column-like. A deep storm might resemble a thick pancake shape, broad but limited in depth compared with its width, or it might resemble a narrower column extending deeper. The shape matters because it affects stability. A broader shallow vortex is more exposed to shear at a wide perimeter. A narrower, deeper vortex has a smaller perimeter relative to its depth, and may be more resistant to erosion. If the Great Red Spot is evolving toward a configuration with a smaller top and a relatively thick depth, it could be moving toward a more stable form even while shrinking in area. The depth question also intersects with Jupiter's internal structure. At great depth, hydrogen becomes more conductive, and magnetic effects can influence flow. The Great Red Spot's measured or inferred depth likely remains above the region where magnetic forces dominate the dynamics in a direct way, but the presence of deeper transitions sets an inner boundary for weather-like motion. It implies that at some depth the atmosphere becomes part of a different regime where conductivity and interior dynamics matter more. The Great Red Spot resides in the regime where weather and jets operate, but its depth places it closer to that inner boundary than a purely surface feature would be. This can contribute to longevity because deeper layers can provide a more stable environment and a slower timescale of change. A deep anchor also helps explain why the storm can maintain strong winds while shrinking. If a large reservoir of momentum exists at depth, the storm can sustain rapid rotation at the boundary of its upper visible region, even as the outermost cloud patterns are stripped away. The visible outline could retreat to a smaller radius, where the remaining circulation is still strong. The storm's energy and momentum might be redistributed rather than simply lost. This is consistent with a vortex that remains alive while shedding its outer shell. Even with depth evidence, it remains uncertain what drives the long-term shrinkage. A deep storm could still shrink if energy input is reduced relative to loss, or if the surrounding jets become more effective at stripping the boundary. Depth does not guarantee growth. It provides resilience. The storm can persist, but it can still evolve. Depth therefore supports a picture in which the Great Red Spot is not vanishing quickly, but is being reshaped by ongoing interactions and boundary losses. The depth evidence also imposes constraints on simple explanations. If the storm is deep, then shrinking cannot be explained solely as a superficial change in high-altitude haze. The storm involves a thick mass of rotating gas. Its evolution must involve changes in that rotation field, not only in the color-bearing layer. The cloud top shrinking remains real, but it is connected to deeper dynamics that store momentum. This pushes the interpretation toward gradual reorganization rather than sudden decay. At the same time, depth evidence does not remove uncertainty about the future. A deep vortex can persist for a long time and still eventually weaken if losses continue and supply does not compensate. It can also stabilize at a smaller size if it reaches a configuration where boundary erosion is balanced by energy input. Observations indicate continued shrinking over the modern era, but it remains uncertain whether the storm will continue to shrink at the same rate, slow its shrinking, or reach a stable smaller size. Depth suggests persistence is plausible, but it does not determine the outcome. This inward layer therefore holds a careful conclusion. Observations indicate that the Great Red Spot has hidden depth, extending far below the visible clouds. This depth likely contributes to its longevity by providing mass and momentum that resist rapid change. It remains uncertain how the depth and deep geometry evolve as the cloud top footprint shrinks. Because depth measurements are limited and require interpretation, the best physical picture is a deep, long-lived vortex whose upper layers are being eroded and reshaped by jets, turbulence, and mixing, while a deeper core continues to sustain rotation. From depth and uncertainty, The path now moves to the specific measurements that modern instruments provide, focusing on how spacecraft and telescopes observe wind, temperature, and depth clues, and how those observations refine the shrinking story without overreaching beyond what data can support. Modern understanding of the Great Red Spot is built from instruments that measure more than pictures. Images provide outline and color, but they do not directly provide depth, temperature profiles, or mass anomalies. Spacecraft and advanced telescopes add those dimensions. They allow the storm to be treated as a physical structure in a three-dimensional atmosphere rather than as a two-dimensional oval. This matters for the shrinking question because it reveals that the storm can remain deep and energetic while its cloud-top footprint contracts, and it provides ways to test which processes are most consistent with the data. One class of measurement is high-resolution imaging across multiple wavelengths. Visible imaging tracks cloud patterns and the movement of features around the storm. Infrared imaging maps temperature at cloud top and above cloud levels. Ultraviolet imaging can highlight hazes and fine particle layers in the upper atmosphere. By combining these, scientists can infer vertical differences. A region that looks bright in one wavelength and dark in another may have different particle sizes, different cloud thickness, or different altitude. The Great Red Spot is a multi-layer feature in such maps. It has a visible red color, a thermal signature, and an ultraviolet haze signature that vary across its interior and boundary. When measurements at the cloud tops come from cloud tracking, features on the storm's periphery move rapidly, and by measuring their displacement between images taken at known times, the wind speed can be inferred. These measurements show the strong circulation around the storm and how it interacts with nearby jets. Over time, changes in wind speed profiles can be tracked. Observations indicate that the Great Red Spot's periphery winds remain strong even as the visible footprint shrinks, and that the storm's shape changes occur alongside continued vigorous rotation. This supports the idea that shrinking is not simply the disappearance of circulation, but a reorganization and boundary retreat. Temperature measurements provide another key dimension. Infrared instruments can measure thermal emission from Jupiter's atmosphere. In the upper troposphere and lower stratosphere, temperature differences reveal vertical motion patterns and wave activity. The Great Red Spot often appears as a distinct thermal feature, reflecting its unique circulation and its influence on surrounding air. Temperature maps can show whether the storm's top is cooler or warmer than surroundings at certain levels, and they can show how the storm influences temperature patterns in its wake. Such observations support the view that the Great Red Spot is not a thin skin. It affects multiple atmospheric levels, and its circulation modifies the thermal structure around it. Spacecraft measurements add depth clues that Earth-based telescopes cannot provide. A spacecraft flying close can measure variations in Jupiter's magnetic field, gravity field, and microwave emission with high precision. For the Great Red Spot, gravity and microwave measurements are especially relevant. These measurements provide evidence that the storm extends downward through a substantial depth. Microwave sensing is valuable because microwaves penetrate beneath the visible clouds. The microwave brightness depends on the absorption of certain gases, particularly ammonia, where ammonia is present in higher abundance. Microwave emission from deeper warm layers is absorbed more, changing the brightness. By measuring microwave emission at multiple wavelengths, different depths can be sampled because different wavelengths penetrate to different levels. A pattern in microwave brightness associated with the Great Red Spot indicates that the storm influences ammonia distribution and temperature at depth. This supports a picture of a deep circulation that mixes material vertically, not merely a surface swirl. Gravity sensing provides another depth constraint. A deep storm involves a mass anomaly, because moving gas can produce density differences and pressure fields that deviate from the background. A spacecraft tracking system can detect tiny changes in velocity during a flyover, indicating a small change in gravitational pull. A detectable gravity signal associated with the Great Red Spot implies that the storm extends deep enough and involves enough mass to influence gravity. This evidence is particularly powerful because gravity responds to mass rather than to cloud traces. It is consistent with a storm that reaches hundreds of kilometers downward, though the exact depth depends on how the gravity signal is interpreted through models of density structure. These spacecraft measurements do not measure depth as a simple ruler measure. They require modeling because the atmosphere is complex, and multiple vertical profiles can produce similar signals. Therefore, uncertainty remains. Yet the combined evidence from microwave and gravity measurements supports the conclusion that the Great Red Spot is deep. This depth helps explain why it persists despite shrinkage at the top. In addition to these direct depth probes, long-term monitoring from Earth and from space-based telescopes provides temporal context. It shows the trend in shrinking, the episodes of filament shedding, and the changes in surrounding jet patterns. A spacecraft flyover provides a snapshot of depth at a particular time. Long-term monitoring provides a continuous story at the cloud tops. When combined, these create a layered timeline. The storm's visible footprint changes slowly, while depth evidence suggests a substantial stable column beneath. The combined picture supports the idea that the storm is slowly losing or reorganizing its outer layers while keeping a deep core. Instrumental measurements also help identify what remains uncertain. One uncertainty is how much the storm's deep structure changes as it shrinks. Depth measurements are not continuous. They occur during particular spacecraft passes. Therefore, it remains uncertain whether the storm's depth has remained constant or has changed over the same decades that the top has shrunk. Another uncertainty is how the storm's vorticity distribution changes with altitude. Winds are measured mainly at cloud tops. Deeper wind profiles are harder to infer. Microwave sensing provides hints through composition patterns, but not a direct map of wind speed. Therefore, the vertical distribution of rotation remains partly inferred. Another uncertainty involves the surrounding jets. Cloud-top wind fields can be mapped and show how jets and the storm interact. Yet whether jet structure changes at depth in the same way is uncertain. If the jets that confine the storm extend deep, changes at the top might be mirrored below. If the jets are shallower, then the deep environment could be more stable than the cloud-top environment. This difference matters for understanding whether shrinking is driven by shallow changes in the confinement corridor or by deeper changes in the vortex itself. Modern instruments also clarify that the Great Red Spot is embedded in broader atmospheric variability. Jupiter's belts can fade and return. New storms can form and merge. The distribution of smaller vortices changes. These changes can alter how often the Great Red Spot is disturbed and how much edge erosion occurs. Monitoring helps correlate episodes of shrinkage acceleration with periods of increased turbulence or with the passage of other vortices. Yet correlation does not fully establish causation, and the system remains complex. Observations indicate interactions and shedding, but the precise energy accounting remains uncertain. The value of the modern instrument view is that it constrains the range of plausible explanations. It rules out simple pictures where the Great Red Spot is a thin surface stain. It supports a picture of a deep vortex with measurable influence below the clouds. It supports a picture where shrinking is a change in cloud-top footprint and boundary structure, rather than an immediate collapse of the circulation. It also supports the idea that the storm remains vigorous in terms of wind speed, even while it becomes smaller. This combination suggests a reorganization toward a compact configuration, possibly reducing boundary losses while retaining a deep core. With the instrument-based picture in place, the inward path can now move to the cautious discussion of the future. The question is not a prediction of an end date. It is a bounded set of possibilities consistent with the evidence continued shrinking, stabilization at a smaller size, or gradual fading through ongoing erosion. The next section will hold those possibilities calmly, based on what is known about the storm's energy balance, depth, and environmental stresses. The future of the Great Red Spot is often framed as a countdown, but the evidence supports a slower and more cautious view. The storm is shrinking in its visible footprint, yet it remains deep and energetically active in its circulation. A vortex can evolve for a long time without vanishing quickly. In a system as large as Jupiter's atmosphere, changes can occur over decades and centuries, and different processes can dominate at different times. The most realistic approach is to describe a small set of bounded possibilities, consistent with known physics and the available measurements, while acknowledging what remains uncertain. One possibility is continued shrinking at the cloud tops. This would mean the storm's visible area and length continue to decrease as boundary erosion and filament shedding gradually remove the outer layers. In this scenario, the storm persists as a coherent vortex but becomes progressively more compact. Continued shrinking could occur if the surrounding jets and turbulence continue to strip the perimeter faster than the vortex can replenish it, or if the storm's environment becomes slightly more erosive over time. The vortex's deep core could remain while the top becomes smaller, producing a storm that is still present but less dominant on Jupiter's face. This possibility is consistent with the long-term trend observed in modern measurements. Yet even if the trend continues, the rate of change may not remain constant. Shrinking can slow as the vortex becomes smaller because the boundary length decreases and the vulnerability of elongated ends is reduced. A compact vortex may shed fewer filaments or shed them less effectively. It may also fit more comfortably within the confinement corridor set by surrounding jets. Therefore, continued shrinking does not necessarily imply a rapid disappearance. It could imply a gradual approach toward a smaller stable size. A second possibility is stabilization at a smaller footprint. In this scenario, the storm reaches a configuration where energy input and energy loss balance at a reduced size. Boundary erosion still occurs, but replenishment through interaction with shear, merging of smaller vortices, and deep coupling is sufficient to maintain the storm's area near a new equilibrium. The storm remains visible and long-lived, but it no longer occupies the large oval area known from earlier centuries. This is a plausible outcome because many vortices in rotating atmospheres can exist in stable states, determined by background shear and by the availability of energy. Jupiter itself hosts other long-lived ovals that are smaller than the Great Red Spot and can persist for years or decades. A stabilized smaller Great Red Spot would fit within this broader behavior. Stabilization would not necessarily mean the storm stops changing. The storm could continue to vary in color, boundary texture, and shape with time, responding to changes in the surrounding belts and to interactions with other storms. It would mean that, on average, its footprint does not continue to contract significantly beyond a certain point. This outcome would be consistent with a deep vortex that remains resilient, and with the idea that shrinking can reduce losses and enhance stability. The difficulty is that the present record has not yet shown a clear leveling off in a way that can be stated with confidence. The record shows variability and a long-term reduction, but the presence or absence of a new equilibrium remains uncertain. A third possibility is gradual fading through ongoing erosion. In this scenario, The storm's deep core eventually weakens because energy losses over time exceed energy input. The vortex could lose vorticity not only at the top but throughout its depth. The cloud top footprint could continue to shrink, and the boundary could become less distinct. Color could fade if the high-altitude haze production weakens or if mixing increases. Eventually, the storm might no longer be identifiable as a distinct long-lived oval, even if smaller vortices continue to exist in the same region. This outcome is physically possible because no vortex is guaranteed to persist forever in a turbulent fluid. Even long-lived features can end if the conditions that maintain them change. This fading scenario requires some sustained shift in balance. It could arise if the surrounding jets change in a way that increases shear and erosion. It could arise if the population of nearby vortices changes, reducing mergers that feed the storm. It could arise if the storm's deep coupling weakens, reducing energy and momentum support. It could also arise through internal changes in the vortex's structure that make it more susceptible to boundary instability. These are plausible pathways, yet they remain uncertain in their likelihood because the mechanisms involve deep atmospheric dynamics that are not fully measured over long time. A key point in all these possibilities is that Jupiter's atmosphere is not static. The belts and zones can undergo changes in brightness and structure. Jet streams can vary. New storms form and merge. The Great Red Spot is embedded in this evolving environment. Therefore, the future is not determined by the storm alone. It is determined by the coupled system, the storm, the jets, the energy flow from below, and the neighborhood turbulence. A stable storm in one background state might shrink in another. A shrinking storm might stabilize if the background becomes less erosive. A storm that appears stable could weaken if a sequence of disturbances removes too much outer vorticity. The evidence that the Great Red Spot has hidden depth adds resilience to the picture. A deep vortex can persist through periods of surface-level disturbance and can maintain coherent circulation even when the cloud top expression changes. This makes rapid disappearance less likely without a major change in the environment. Yet depth does not guarantee permanence. A deep vortex can still lose energy and vorticity through processes that act over long time. The likely timescale of major change remains measured in decades rather than in days, consistent with the observed shrinking trend. It is also important to separate visibility from existence. A storm could still exist as a deep circulation even if its cloud top color and contrast diminish. If haze production changes, or if the storm's top becomes less distinct, it might become harder to recognize in visible images, even while a deep vortex persists. Conversely, a storm might remain visible but become shallower, without continuous depth probing. These possibilities cannot be distinguished easily. Therefore, statements about the storm's future must be made cautiously, with attention to what is actually measured. The measured shrinking is a change in the cloud top footprint. The deep structure is inferred from limited passes and models. The coupling between the two remains uncertain. Within consensus science, the most grounded conclusion is that the Great Red Spot is evolving rather than collapsing. It is shrinking at the top while remaining dynamically active. It may continue to shrink. It may stabilize at a smaller size, or it may gradually fade over a longer span. The data do not support a precise prediction of when it will vanish, and the physics suggests that the system can settle into different states depending on its environment. The most practical expectation is continued change, monitored over time, with the possibility that the storm remains a feature of Jupiter's atmosphere in a smaller, tighter form. Future measurements will refine this picture. Continued imaging will track size, shape, color, and filament shedding. Wind measurements will track boundary speed changes. Infrared and ultraviolet monitoring will track thermal and haze changes. Spacecraft measurements, when available, will provide further depth constraints. These observations will not force the storm into a simple narrative. They will reveal whether the shrinking trend slows, accelerates, or transitions into a new stable state. Until then, the best approach remains to hold the possibilities without forcing a conclusion beyond evidence. With the future bounded in this calm way, the inward path can now close by synthesizing the full picture. The Great Red Spot is a deep, long-lived vortex confined by jets, reshaped by turbulence, and slowly eroded at its edges. Shrinking is the visible outcome of this balance. The final section gathers these processes into a steady explanation of what is really happening, without exaggeration and without predicting beyond what is known. Jupiter's Great Red Spot shrinks at the cloud tops because it is a living structure in a moving atmosphere. It is not a permanent mark and not a single event. It is a vortex, a coherent region of rotating gas confined within strong jet streams and continually shaped by shear, turbulence, and mixing. The shrinking is real in measured outline and area, yet the storm remains deep and energetic enough to persist. What is really happening is a slow adjustment of a long-lived vortex toward a different configuration, guided by the balance between how it is fed and how it is eroded. At the wider scale, Jupiter sets the conditions. It is massive, rapidly rotating and internally heated. Its atmosphere is deep, layered, and largely free of solid surface friction. These properties allow long-lived storms. Fast rotation organizes the flow into belts and zones, and those belts are tied to alternating jet streams that circle the planet. The Great Red Spot sits between two opposing jets that confine it in latitude. The jets act like walls and like blades at the same time. They keep the storm from drifting far, and they shear its boundary continuously. This confinement corridor shapes the storm's width and helps define the space where it can remain stable. Within that corridor, the storm's size is not fixed. The boundary is where the storm meets the surrounding jets and smaller eddies. It is a region of strong wind gradients and frequent instabilities. The Great Red Spot's perimeter can stretch into streamers that peel away and are carried off by the jets. It can shed reddish filaments and flakes that drift into the belts, fade, and mix. Each event is small compared with a full storm. Yet over many years such losses accumulate. Shrinking is the cumulative retreat of the visible boundary as outer layers are stripped more often than they are rebuilt. The neighborhood around the storm contributes to this process. Smaller vortices form and drift with the jets. Some merge into the Great Red Spot and add organized rotation. Others graze the edge and pull away filaments without merging. Turbulence in the wake region behind the storm is continually created as the jets bend around the vortex. This turbulence produces small eddies that can further disturb the boundary. The storm and its environment form a loop. The storm modifies the flow. The modified flow creates turbulence and smaller vortices. Those features then interact with the storm, shaping its perimeter and influencing how quickly it loses its outermost structure. Energy supply explains why the storm persists while shrinking. Jupiter emits more energy than it receives from the Sun, indicating internal heat rising from within. This heat drives convection and helps maintain a vigorous atmosphere. The Great Red Spot can draw energy from several pathways, interactions with background shear, absorption of smaller vortices, and coupling to deeper atmospheric motions. At the same time, it loses energy through boundary turbulence and mixing, and through the general dissipation of organized motion into smaller-scale turbulence. If supply is sufficient for the core but insufficient to maintain a broad footprint against boundary losses, the The storm can persist but become smaller. A smaller storm has a shorter boundary, which can reduce the total area where losses occur. Shrinking can therefore be a stable adaptation, a way for the vortex to remain coherent under continued stress. Depth ties the surface story to a deeper resilience. Evidence from modern measurements indicates that the Great Red Spot extends far below the visible clouds, reaching into denser layers of Jupiter's atmosphere. A deep vortex carries more mass in motion, and therefore more momentum. This makes it resistant to rapid change. The cloud-top footprint can shrink as outer layers are stripped. While the deeper circulation continues to support the vortex's core, depth does not mean the storm is immune to change. It means that change is slow, and that the storm can survive many surface-level disturbances without collapsing. The storm's changing shape fits naturally into this picture. The historical storm is more elongated. The modern storm becomes more compact and more rounded. Elongated ends are exposed to shear and are vulnerable to stripping. As those ends are eroded, the storm's aspect ratio decreases. The boundary retreats to a tighter oval. The remaining vortex can still have strong winds around its perimeter. Its color can vary depending on haze chemistry, vertical lifting, and mixing. Color changes can accompany structural change because the storm's vertical circulation and boundary permeability influence how haze particles are produced and retained. Yet color is not a direct measure of storm strength. It is a clue to altitude and chemistry. Spacecraft and telescopes refine this calm physical picture by adding measurements of wind, temperature, and depth-related signals. Cloud tracking shows persistent strong circulation. Thermal mapping shows a distinct storm-related structure in the atmosphere. Microwave and gravity evidence indicates hidden depth. Together, these measurements support a consistent interpretation. The Great Red Spot is not simply fading away at the surface. It is being reshaped by its environment and slowly losing outer material, while a deep core continues to rotate. What remains uncertain is the precise balance of processes at any moment. It remains uncertain how much of the long-term shrinkage is driven by changes in the surrounding jets versus internal reorganization of the vortex. It remains uncertain how the storm's deep structure changes over decades because depth measurements are limited in time. It remains uncertain whether the storm will continue shrinking at the same pace, slow and stabilize at a smaller size, or gradually fade in the longer term. The evidence supports continued evolution rather than a sudden end, and it supports the idea that the storm's deep nature makes rapid disappearance unlikely without a significant shift in environmental conditions. The most reliable conclusion is simple and steady. The Great Red Spot shrinks at the cloud tops because its edges are continually eroded by shear, turbulence, and mixing in Jupiter's banded jet system. It survives because it remains a deep vortex in a planet powered by internal heat and organized by rapid rotation. The storm is a long-lived structure adjusting to a changing flow around it, shedding its outer layers and tightening into a smaller form. The change is real, measured, and gradual, and it belongs to the natural behavior of a giant planet atmosphere.